Let me tell you a little bit of background on myself and how I think that I'm somewhat qualified to stand up here and talk about both the Windows kernel and the Linux kernel. I've got a background in computer engineering. Got an undergraduate degree, a master's degree, and a PhD in computer engineering. My PhD is from Carnegie Mellon University, a school in the United States, where during my doctoral work I actually was working on a flavor of Unix called BSD, running on top of the Mach microkernel operating system. So my background through research and through school was on Unix. I came out of school and then started to work on the Windows platform. Several years after I graduated, I went to IBM Research in the United States. And at IBM Research, I was hired specifically for my knowledge of Windows internals. But while I was there, I started to look at what was going on in the Linux side of things and becoming familiar with how the Linux kernel architecture is composed and its capabilities, and became somewhat a Linux resource within IBM Research as well. In fact, there was several years ago an underground effort within IBM to port Linux to the S390 mainframe, and that's actually a project that started in Germany. Well, IBM at that point had to decide whether they wanted to commercialize this thing, what they wanted to do with this port of Linux, and so they formed a committee that would advise Lou Gerstner, who was the chairman of IBM at the time, as to what to do with this version of Linux. And I was the technical Linux expert on that committee, which was composed of about 8 or 9 people and several people from marketing and other business groups within IBM. I also served as the Linux technical resource for the AIX division of IBM, AIX being IBM's version of Unix. And they, of course, were interested in what was going on with Linux when I was there. I'm no longer at IBM. But that just gives you a background into how I started looking at Linux. I've been following the developments of Linux for a long time. And the class that I'm going to give you today, or the session that I'm going to present to you today, is actually a session that I've asked for input from all the major players that it relates to. So for example, David Cutler, who, as I'll tell you, is the chief architect of Windows NT and still works at Microsoft on the Windows kernel, he's reviewed the slides. Linus Torvalds has reviewed the slides, and I've had several other developers from the Windows team and from the Linux team review the slides and provide me their feedback. And I've incorporated all their feedback. At the end of the session, actually, I'm going to show you an email that I got from Linus as we were talking about the session, where he points out the problems he has with this, with what I'm going to tell you, and I'll address those, what he says then. So now, this is the outline of the talk. And this is a very technical talk, so as well as getting a comparison of the two operating systems, I'm going to give you a heavy dose of Windows internals and Linux internals. But first I'll start by talking about the evolution of the operating systems as they progressed through time, when they were developed, where you can trace their roots back to, and talk about where we are now with those operating systems. Then I'm going to take a very high-level look at the two architectures. And after that high-level look, dive in a little bit deeper and start to compare some of the kernel mode subsystems. So talk about how scheduling works on Linux, how it works on Windows, what's different, how memory manager is different, and the same between the two OSs. And the section following that one, I'm going to talk about a number of features that I've seen go into Linux, a number of enhancements and capabilities that have been added to Linux over time that actually make it look a lot more like Windows in terms of Windows having had those same capabilities or features for a long time. Now Linux progressively getting more and more of them. The two operating systems started out looking kind of the same, which might be surprising to you, as you'll see, and have actually evolved to look more and more the same from a kernel perspective. Then I'll talk about where we are in terms of the performance of the two kernels, because of course kernels are designed to manage the resources of the computer and to manage them as efficiently as possible so the applications can perform as efficiently as possible. So in terms of saying what's a good kernel versus not a good kernel, you've got to talk about how applications can utilize the kernel services to do what they want to do. And one way that people measure that is through benchmarks. So I'm going to present to you the current state of the world in terms of benchmarks of Linux versus Windows. And then I'll spend a few minutes just pontificating, if you'll indulge me, about where I think Linux is going, where I think Windows kernel is going, and what's the future hold. So let's start with, before even I get into the history, narrowing the scope. And in an hour and 15 minutes, I have a limited amount of time to even cover the material I'm covering. I certainly can't cover all the things that you might be interested in hearing about with respect to Linux versus Windows, including the cost, the total cost of ownership, how supportable the two OSs are, what kinds of applications are available for the two OSs, how manageable they are, and their use as a desktop system. Those are all outside the scope of this talk. And so I'm focusing just on kernel level technology. And I'll talk about where that fits into the big picture at the end of the talk. So if you look at Linux and try to figure out where it came from, you of course have to look back at the Unix operating system, which it's somewhat derived from. So in that sense, the real history of Linux starts back in 1969 when Ken Thompson developed the first version of Unix at Bell Laboratories at AT&T. A few years later, Dennis Ritchie, who designed the C programming language, he's the father of C, he joined the project, and they both debuted in a joint paper to the academic community at a conference in 1974, a paper on Unix. And Bell Labs, a couple years later, released the first commercial version, which was called Unix version 6. Well, Unix, Bell Labs was pretty liberal about letting universities and companies license Unix source code and use it within organizations, and so it began to spread pretty fast. And in 1978, they actually released a version called the Unix time-sharing system, which is a version with the source configured so that portability would be very easy. So it'd be easy for somebody that said, hey, I want to take Unix and run it on this different kind of processor and port it. And that enhanced the proliferation as well. So because the source code was proliferated, people could license it, what you saw was three major branches of the Unix tree develop as companies started to add their own features and capabilities to Unix. And those three branches were Unix System 3 from Bell Labs' own Unix support group, another version called Unix BSD from the University of California at Berkeley, and finally, believe it or not, Microsoft's own version of Unix, which was called Xenix. And if you're surprised that Microsoft had its own version of Unix, you might be even more surprised to know that if you look at the early 1980s and talk about the biggest Unix vendor in terms of units deployed around the world, that vendor was Microsoft. Now, what happened to Microsoft Xenix, and I think just as a little sidebar, because it kind of brings us into current events, Microsoft Xenix was actually sold off to SCO. SCO was actually started with Microsoft Xenix. And the SCO group, Santa Cruz operation, because Microsoft gave them Xenix, Microsoft took partial ownership of SCO, which Microsoft eventually sold off in the early 1990s. And now you know that if you've been following what's been going on in the US with SCO, and SCO challenging the legitimacy of copyrights of various pieces of the Linux source code, and Microsoft turns out is funding indirectly SCO's operation in challenging Linux. It's kind of a, I kind of look at it as a father looking after a child that's gone off and trying to help them out after they've left the house. So the three branches continued to fragment even further. Those were the three major branches. You had lots of offshoots. There was a couple of efforts as the industry started to recognize that this diversity was going to cause a problem, because you've got these vendors that put in special features into a version of Unix. Now you have applications that only work on that particular version of Unix. If the user of Unix wanted to switch to a different version of Unix, well, then they'd be kind of stuck because their applications were coded to use those special features. And so two efforts were started to kind of define what would be the definition of Unix. And so hopefully application vendors would program to this definition of Unix, which all the major Unix variants would support, and you'd have cross-platform portability. Those two efforts were, one was IEEE POSIX, which released a standard API interface for Unix, and another one was the X-Open Group's portability guide, which also defined the way the services that Unix operating systems should make available to applications. Well, even though those portability guides were released, you still saw a lot of fragmentation in Unix, and you still see that today. So let's pick up now where Linus comes into play. In 1991, Linus took a college computer science course that used a toy operating system called Minix that was modeled after, or that is modeled, it's still available, it's modeled after Unix. It's a very stripped down, basic, bare bones version of Unix that's simple enough so that a university student can understand it from top to bottom in one semester. Fits on a floppy disk, it's that small. And Linus, after taking the course, was thrilled with this access to the source code for this thing and how he thinking how he could make it better and make it portable, make it run on a whole bunch of different platforms. And he approached Andrew Tannenbaum, who's the author of the tool and the author of the textbook that Linus was working off of. Andrew Tannenbaum, by the way, lives here in Amsterdam. He's not here right now. I invited him to this class. Actually, he is on a trip in the US, unfortunately. But in any case, Linus contacted Andrew and said, Andrew, you know, I think your Minix operating system is really pretty cool. How about if I take it and I make it better? And Andrew flat out said, no, I'm not going to allow you to do that, because I want to keep this thing as simple as possible so that university students can understand it. If you start to go add to it, it won't be teachable in one semester class. So Linus, discouraged, went off on his own and started to make his own version of a Unix-like operating system. In October 1991, he announced Linux version 0.2, and in March 1994, he released version 1.0, so the first big version. Let's turn our attention now to Windows NT, talk about its history. And if you look at the history of Windows NT, you've got to even go back further than the original release, back to Digital, the company that used to be Digital, where in the mid-1970s, 3 people architected an operating system for Digital called VMS. And those 3 people were Dick Husvet, Peter Lippmann, and David Cutler. The VMS operating system was targeted at Digital's 32-bit VAX processor, and Digital shipped the first version in 1978, right around the time the first version of Unix was released. Well, so David Cutler moved to Seattle in the late 1980s and opened a development facility there called Deck West that was going to work on a new operating system called Mica for a new CPU codenamed Prism. And the work that came out of Prism actually ended up, part of it, in the Alpha processor. But the project was canceled after a couple of years. So David Cutler, being somewhat discouraged, was kind of looking around at other opportunities. And that's where Microsoft comes into play. Bill Gates, seeing that Dave was probably disenchanted with Digital, invited him over. And conveniently, he was just down the street, invited him to a meeting, and hired Cutler and 20 engineers from the Deck West facility. In fact, some of those were hardware engineers. So that's where the Microsoft hardware division actually sprang from, is the fact that Microsoft had these hardware people from Digital that they needed to find something to do. Well, this new project that Bill had assigned Dave to work on was called NT-OS2, New Technology OS2. It was New Technology OS2 because Microsoft was good partners then with IBM and wanted to make a robust version of the OS2 operating system that they would own. Well, in 1990, Microsoft released Windows 3.0, which was the first really successful version of the Windows 16-bit operating system. It just had a huge popularity as it was released, and so Microsoft and Bill Gates specifically said, hey, why don't we forget this partnership with IBM, and let's go do this thing. Let's focus on Windows. And so the project was renamed Windows NT. That was going to be the primary operating system interface that would be supported as a new version of the Windows API that was supported by Windows 3.1. And Microsoft released Windows NT 3.1. The version number was made to coincide with the current version of the 16-bit Windows operating system, which was 3.1, in August of 1993. So if you look at a timeline of the evolution of these two operating systems, starting with their predecessors, you see that they've both had their birth back in the mid-1970s, and they both now have had their origins back in the mid-1970s. They both had their birth in the early 1990s, and they've been evolving pretty quickly since then. And my point in showing you this is that the two operating systems, as I'm going to show you in this presentation, are very similar from a kernel perspective, and that's not, I think, an accident. It's because of their common evolution in time. As engineers work on problems, they look around and see what's going on elsewhere, and they take the good ideas and put them into what they're doing. And so the fact that these evolved at the same time, you're going to have a lot of the same similarities between the two. So, by the way, for those of you that haven't seen a picture of David Cutler, this is myself and David Solomon at David Cutler's house a few weeks ago. He's in the middle, Dave Cutler's in the middle. And for those of you that haven't seen a picture of Linus, this is Linus. Actually, this is Linus. I got dinged at this for Tech Ed US. People didn't like me showing this. They said that I was, being mean to Linus. But Linus did this as a dunking competition, dunking for charity in Australia at Linux World earlier this year. And somebody posted this picture of him on the net, so I just thought it would be humorous. Now, when we were at David Cutler's house, I told him that I was presenting this at TechEd, and I said, David, you know, it'd only be fair if I show a picture of you in briefs at the conference, and can I take a picture of you like that? And of course, you can imagine his answer. So I don't have a picture of David Cutler like that for you to show you, but I would if I could. So let's take a look at the architectures now. First of all, the broadest way you can categorize an operating system is how it divides up its work. And if you look at Windows and Linux from that point of view, they're both considered monolithic operating systems. That means that all of the core operating system services run in the same address space. And the easiest way to kind of understand what I mean by that is to consider the total opposite of a monolithic operating system, which is called a microkernel operating system. Andrew Tannenbaum's Minix operating system, for example, is a microkernel-based operating system. And in that kind of operating system, the kernel itself is very tiny and provides a very core set of services. And other subsystems that you commonly think of as being part of the kernel, like the memory manager, the process manager, which does scheduling, they're running in their own address spaces. They look a lot like user mode programs. They look a lot like programs. The idea behind microkernel is that if one of those fails, you can restart it. They've got nice interfaces, so it's easy to replace one of these modules with a different version that has a different implementation. The problem with a microkernel-based operating system is performance, because when they want to communicate with each other, they've got to transmit messages between each other, because they're in different address spaces. They can't read each other's memory. And that transmission of messages causes a performance hit. So most commercial operating systems are monolithic, including Windows and Linux. If you've heard of OS X, Apple's operating system, and know that it's based on the Mach operating system from Carnegie Mellon, Mach is a microkernel-based operating system. OS X takes the Mach kernel and makes it into a monolithic operating system. So OS X really isn't an example of a microkernel-based operating system that you might think. Now, at the highest level, when you compare the two operating systems, the only real thing that you see is different is windowing, the way windowing is handled. So Windows has a kernel mode windowing subsystem, and Linux has a user mode X windowing system. So this is Windows, the high-level architecture, where you've got the core set of drivers and services here executing in their shared address space in the kernel. You've got an application up here in user mode. When it wants to perform a graphics operation, like draw to the screen or create a window or create a menu, it does a call into the kernel, into the Win32 windowing subsystem. If you look at Linux, the architecture looks like this, where you've got the application up here, and when it does a windowing call, it sends a message to the X window process, which looks like any other process, user mode process. Now, what are the advantages or disadvantages of these two approaches? Well, with this approach, you don't have a message. You have a simple transition from user mode to kernel mode, whereas here you've got messages that are being transmitted, which can degrade performance. And there's a lot of tricks that X Windows does to try to minimize that. An advantage of the X Windows approach is that it makes it very easy to remote an application, something you can't do on Windows. You can't run Word remotely from another machine and see the window come up on a different machine. You've got a terminal server in and get a whole desktop is the only remote capability Windows has. And with X Windows, you can run apps, just the windows for the apps, on a remote client. So that's an advantage there. So when we compare the architectures, I've broken it down into various subsections. We're going to talk about processes and scheduling, symmetric multiprocessing support, memory management, the I/O system, file caching, and security. In process management, well, the definition of a process in Windows is a container, and that container has a few things associated with it, including an address space that holds the code and data of the program that's being executed in that process. It also has a list of resources that are opened by that process, and resources can include files and registry keys, and it also has at least one thread. A thread is what actually executes the code, not the process. The process has to have a thread within it to execute. So the scheduler, when it decides who's going to run, will pick a thread to run, and that thread belongs to a process. So you can think of that process as running when it's actually a thread within that process. There's no inherent parent-child relationship between processes and their children processes they create in Windows. And threads, being the basic scheduling unit, are what the scheduler looks at. It looks at the priorities of the threads to decide what to pick next to run on the CPU. Windows also has what are called user mode threads, or lightweight threads, which are called fibers. And fibers are actually made without any support of the operating system itself. They're totally up in user space. It's where an application basically becomes its own scheduler. If you look at Linux, the process management there, what you're going to see here on this first slide, let me describe this to you, is the orange text are things that are different from Windows. So everything that's white is the same, and the things that are orange are different. So in Linux, though, when you talk about a process, things get a little confusing because of a design decision Linus took a few years ago. A process in Linux is known as a task. And the task looks like a Windows process. It has an address space. It has a table of resources to open resources. And it has statistics. However, there is a parent-child relationship between tasks. When one task creates another task, that child task isn't going to terminate until somebody asks what its return status is, what its exit status is. By default, that's supposed to be the parent task. Now, if a parent doesn't ask, Windows has this background daemon task that goes and just does that for the parent. It's also, however, the basic scheduling unit. So a task is the equivalent of a Windows process. A task is also the equivalent of a Windows thread. It depends on how the task was created. So let me explain this. In Windows, you've got a process, and that process has multiple threads. Those threads, if it's a multi-threaded process, share all the address space, share the resources of the process that they belong to. On Linux, you can have a task that it's composed of multiple tasks that all share the same address space, handle table, and so on. But if a task creates another task and says that it doesn't want to share anything with that other task, that task ends up looking like a new Windows process with one thread in it. The system call that's used to create a new task is called clone, and the clone call tells the Linux what aspects of the parent task the child task is going to share. So basically, a task creating another task that shares nothing is the equivalent of creating a new process, and a task creating another task that shares everything is the Windows equivalent of creating a new thread. So there are no threads per se, even though I'm going to be referring to threads as we go through this talk just for clarity. Linux also has pthreads, which are cooperative Unix user mode threads that most recently were added and that are POSIX compliant, something that the Linux community is very happy about. So let's talk about scheduling now. How does the system decide what to run on the CPU? I mentioned that it has to do with priorities, and there's two scheduling classes on Windows. If you look at the priority spectrum, the top half is called the real-time or fixed priority range. Their priority number is 16 to 31, and the bottom half is priority numbers 1 to 15, and it's called the dynamic priority class. The reason that it's called dynamic and the top part is called fixed or real-time is that the scheduler itself in the system can change the priorities of threads that are executing within that dynamic priority class. So the scheduler, for instance, will give a thread a boost if it wakes up waiting for an event and it's been sleeping for a while. And it gives it a boost to try to kind of be fair for that task, that it's competing for CPU with other tasks that are just sitting there hogging the CPU. If you give the task that was sleeping a boost, now it has a better chance of running because its priority will likely be higher than those other threads that were hogging the CPU. So the model is, and the real time, of course, that means that the scheduler is not going to be messing with the priorities of the threads running in that range. They're going to be left at whatever they were. Higher priorities are favored in Windows, as you've gathered. So 31 is the highest priority. Thread priorities are never lowered below the level they started at. So if a thread starts out at priority 8, which is the default priority for a thread in Windows, and it gets a boost up to 10, it's eventually going to decay back down to 8. It will never be lowered below 8. Linux has 3 scheduling classes instead of 2. The normal scheduling class is priority numbers 100 to 139, and then it has 2 fixed classes, one that's called fixed round robin, which internally are priorities 0 to 100, and fixed FIFO, which internally are priorities 0 to 100 as well. Normal is kind of like Windows dynamic range, where tasks, Windows threads that are Linux threads that are executing that range can have their priorities modified. Now, what's different is that the lower priority number is favored. So the highest priority on a Linux system is actually 0. In the normal class, it would be 100, would be the highest priority in the normal class. And thread priorities can go up and down instead of in Windows where they only can go up. They can, in Linux, go below their starting priority if they start out in the normal class. The way that Linux does this is by, as a thread uses more and more CPU, its priority gets lowered, not in number, but in value. And so it has a less likely chance of getting scheduled, whereas the threads that are sleeping for a long time and not consuming the CPU, well, their priorities are going to be raised. So it accomplishes the same goal as Windows does by trying to give those threads that aren't consuming CPU a better chance at getting the CPU by modifying their priorities. Now, I know a question that you've got probably right now and that you're going to have through the rest of this presentation is which of these approaches is better? And that's a very, very difficult question to answer, and I can't answer that actually, because it depends on the workload and a whole bunch of other things. What I can say is, just looking at these two implementations, the Windows implementation is a lot more rigid. The Linux implementation is a lot more fluid, where priorities can go be modified up and down and kind of track more closely how a process uses how a task rather uses the CPU. When the scheduler decides to schedule a thread on a CPU, it gives that thread a turn on the CPU, and that turn is called a quantum or time slice. After which, when that quantum or time slice expires, if the thread hasn't given up the CPU voluntarily, the scheduler will look and say, is there another thread that I should run on the CPU instead of you? Another thread of the same priority. If a thread of a higher priority becomes able to run, the scheduler is going to go run that thread instead right away. But if there's no other higher priority thread, that thread is going to finish its quantum. The scheduler is going to wake up. And by default, this quantums or turns on a Windows system is 10 milliseconds, anywhere between 10 milliseconds and 120 milliseconds. Actually, there's several preset values in that range. And the reason I can't tell you which value Windows uses is it depends on a number of factors. First of all, whether you're on a professional system or a server system. And second, how you've configured the system to tune itself. If you're on a server system, by default, all the threads have 120 millisecond time slices. If you're on a workstation system, there's two priorities usually involved. One for foreground threads, where foreground threads, I mean the threads that own windows that are visible to you on the desktop, those threads will have longer quantums than threads that are in the background. And those threads might have 120 millisecond or 60 millisecond quantum. The threads in the background might have lower, 10 or 20 millisecond quantums. The scheduler itself is reentrant and preemptible. And what that means is that if you've got a multiprocessor system, the scheduler can be running on multiple CPUs making decisions about scheduling for the operating system. And it's preemptible as well, the kernel. So what that means is if you enter in kernel mode, and a thread's executing in kernel mode, the scheduler can stop that thread, freeze it, and then switch execution to another thread that might even be a user mode thread related to an application like Notepad. And then that thread might come into kernel mode, and the same thing might happen to it. So it doesn't care where a thread's executing when it makes a scheduling decision. If you look at Linux time slices, you see something that's very similar. The time slice, the quantum, can vary between 10 and 200 milliseconds. The default is 100 milliseconds, so that's pretty close to what you see on Windows. But the difference is that the quantum of a thread, even a given thread, can vary across that entire range of 10 to 200. The way that happens is the quantum of a thread in Linux is tied to the priority of a thread. The higher the priority, meaning the more likely it is to be scheduled, the lower the quantum. Because if there's higher priority threads, it wants to give the low priority threads, when they get a chance to execute, a long time to execute, since the higher priority threads are likely to be running more frequently because they're going to be the ones chosen more. So if your priority goes up, your quantum gets smaller. If your priority goes down, your quantum gets longer on Linux. So again, if you look at the two, Windows is a kind of rigid system with just a few options, and Linux is a lot more fluid, trying to take into account how threads are using the CPU. In the multiprocessor support area, Windows, of course, is a multiprocessing OS. It supports up to 32-bit processors on 32-bit systems, up to 64 on 64-bit systems. Symmetric multiprocessing means that all the processors can access all of physical memory, versus processors having their own private physical memory that's not accessible from another CPU. Also, all processors can take interrupts from hardware devices. It also supports non-uniform memory access systems, which is a variant on a symmetric multiprocessor. In a NUMA system, An individual processor has its own local physical memory, or group of processors might have their own local physical memory. Other processors can still access that physical memory that belongs to a different group of processors, but it takes longer to access remote memory than it does local memory. So it's still SMP, just differences in memory access, depending on where you're coming from. The scheduler has to be aware of NUMA systems, because what you don't want happening is having a thread that's executing on a particular node of the NUMA system, accessing its data in that physical memory, loading up that local physical memory with its own data, and then having the scheduler move it across the NUMA system to a different node. Now that thread, when it wants to access its data, has to go reaching across the system, something that you want to avoid. So the scheduler tries to keep threads on the nodes they're running on. The memory manager also is aware of NUMA systems, and when a thread allocates memory, it tries to give it physical memory from that node it's running on when possible. Windows also supports hyperthreading. It's called hyperthreading, or XMT processing, and that's where the processor actually is a single processor, but it appears to the system as two processors. Intel Pentium 4 Xeon systems come in this flavor, and the scheduler has to be aware of this kind of configuration, because if you have two physical processors that look like four system processors to the operating system, you can have a scenario where there's a thread busy on one of those physical processors, busy on the, let's say, logical processor 0. That second physical processor is totally idle, and so is that second logical processor of that first physical processor. Now, the scheduler, when it has another thread to execute, has a choice as to which of these three logical idle CPUs it can schedule that thing on. And what you don't want to have the scheduler do is to schedule it on that second logical processor of that physical one that's already busy, because then that thread's going to be competing with that other thread that's already running. You want the scheduler to put it on that second physical processor that's totally idle. So the scheduler has some smarts about hyperthreading built into it. Linux also supports SMP, whereas Windows has these upper limits built into it of number of CPUs it can support. And this, by support, I just mean run on. I don't mean use effectively necessarily. Linux has no upper limit. It's a compile time option, so you can go download Linux source code and compile it for however many processors you want. There's actually a version of the Itanium source tree for a particular SGI machine in the Linux source kernel, and the source is 2.6 kernel, most recent one, that's predefined to support to run on a 512 CPU system, even though no such system really exists. All CPUs can take interrupts. It supports non-uniform memory access. The place where it's different from Windows support for NUMA systems is that the memory manager hasn't been made aware of NUMA. The scheduler has, but the memory manager doesn't try to allocate memory from local nodes. It also supports hyperthreading, just like Windows does. If you look at virtual memory management, Windows, if you look at 32-bit Windows, splits the user mode address space, or splits the 32-bit address space into a portion that's going to be used by the operating system and a portion that's going to be used by processes, user mode processes that run, like Notepad and Word and so on. And that split by default is right in half. 2 gigabytes of that 4 gigabyte address space are usable by the applications. 2 gigabytes are going to be used by the system, by the operating system and drivers. Here's a picture down here that shows that default split. And so what you've got are different user mode address spaces. Whenever a thread from a different process runs, Windows Memory Manager swaps whatever's mapped into this 2 gigabytes with the address space of the process that it's scheduling, like Notepad. It supports all the features that you'd expect out of a modern memory management subsystem, and all the features you'd expect and more, actually. It supports 32-bit or 64-bit, so there's a 64-bit version of Windows. It supports copy on write, so that applications can share memory, and then when they modify it, it becomes private to them, the modifications. It supports shared memory, so applications can share data easily. And it supports memory map files, which are used for image execution, for example, like running a program is mapped into the address space of the executable. On the Linux side, it also, in the 32-bit version, splits the address space between the system and user mode processes. The default split, though, instead of being 2 gigabytes like in Windows, is 1 gigabyte for the kernel, 3 gigabytes for user mode. You can actually move that line anywhere between those 2 points. of having the operating system have 1 gigabyte anywhere to 3 gigabytes, with the remainder going to user mode processes. And I failed to mention that on Server 2003, you can also move that line anywhere between 2 gigabytes and 3 gigabytes on Windows. So that's very similar usage of those address spaces. Where things are different are that there's a version of Linux, Linux Red Hat Enterprise Edition, version 3, that supports a different split. It's called the 4.4 option, or 4.4 split, where the user mode processes all have an entire 4 gigabyte address space, and the system process all has an entire 4 gigabyte address space. So they've got a lot more memory, a lot more virtual memory to play with, which is good for memory-intensive applications like database servers or web servers. Where you get a disadvantage with that approach is that anytime the user mode process wants to call in a service from the kernel, this memory manager has to switch the address spaces, something that's an expensive operation. So 4.4 split, as long as the application doesn't make many trips into the kernel, is a performance advantage. Otherwise, you're going to be paying a heavy price for it. Linus is resistant to put that into the mainstream kernel, by the way. That's a Red Hat specific enhancement. The Linux Memory Manager supports all the things you'd expect, just like a Windows Memory Manager of 32-bit or 64-bit, copy and write shared memory, and memory map files. So that's the way that Windows and Linux manage the virtual memory of the processes running on the machine. Let's talk about how they manage the physical memory. So physical memory management means you've got a fixed amount of physical memory. What processes do you let use that physical memory? Your goal is to give physical memory to the processes that need it the most, the ones that are most memory hungry and actively using their memory. Processes that aren't using physical memory or that are idle, you want to take paid memory away from those guys and give it to the guys that need it. What you do with the pages you've taken away, the data that was stored there, is send it off to the paging file and then bring it back when you need it, when that application wants to access it again. One of the policies that a memory manager designer has to decide on is when a process needs another piece of memory, another page of memory, where that page of memory should come from, where that physical piece of memory should come from, who should steal it from if all the physical memory is in use. Windows has what's called a per process working sets, where a working set is the list of physical memory assigned to that process. And the page replacement algorithm, the algorithm the memory manager uses to decide who to steal a piece of physical memory from to give it to a process needing another page, is called local page replacement. And so here's a picture of local page replacement. This process here wants another page of physical memory. And what the memory manager does when it decides this process has gotten big enough and there's no more free memory on the system, it's organized the memory that process is accessed from most recent to least recent. And it will take the least recently accessed, the one that the memory that the process has accessed most distantly in the past, figuring it's not going to need it again in the near future, and steals that page away from that process, giving it back to it to use for whatever it wants to use new memory for. Now, the other processes also have their working sets on these lists that are sorted that way. But Windows will steal from the process that wants the new memory. That's in contrast to Linux memory management, where it uses a global working set algorithm, where it also sorts the list of pages of physical memory on the same least recently to most recently accessed